أهلا وسهلا بكم. Welcome back at the second and third sessions. Second session is entitled IoT and Smart Systems. And the third session is entitled Circuits and Communication Systems. So we start now with the second session, IoT, Internet of Things and Smart Systems. This session is chaired by Dr. Ahmed Issa, and he is live with us.
Assalamu alaikum.
Walaikum assalam. So we have in this session 1, 2, 3, 4, 5, 6 papers. A huge task for you.
Yes, I hope I'm ready.
Okay. So we hope the audience are joining us now. We have nearly 40 attendees now. And if there are presenters, I ask them kindly to wave so we can recognize them and add them as panelists. Also, we have Dr. Assam Ishaq, and he also will be maybe responsible for answering questions regarding his papers. He is also with us.
Thank you, yes, I'm here.
Okay, Dr. Ahmed, you can maybe start presenting the first paper while I upload or prepare the presentation for play.
Sure. Yeah. Well, first of all, good afternoon, ladies and gentlemen. I'm very honored to participate in ICPET for the fourth year in a row. This year, I'm participating as a session chair. The first paper in this very rich session will be presented by Mr. Fadi Abdelhaq, and he's presenting his work entitled Wireless Sensor Network for Traffic Monitoring. And this paper is co-authored by Dr. Adnan Salman. Our presenter for this paper, Mr. Muhammad Abdelhaq, received his BSc degree in software engineering from Philadelphia University in Jordan, and his master's degree in advanced computing from Al-Najah National University in Palestine. His research interests are mainly in the areas of sensors and control systems. He's working as a part-time lecturer in the Department of Computer and Information Technology at Rauda University College in Nablus, and he also works as a programmer and a technical advisor at the Health Master Company in Nablus, Palestine. So if the presenter is with us live today, may raise his hand to present, or alternatively, Dr. Aiz, you may, if you don't mind, start playing the video.
The video is ready, but I want to see if he's with us so we can promote him as a panelist.
Yeah.
Okay, Fadi. So is Fadi with us? Muhammad Fadi.
Muhammad Fadi.
Yeah. Yes.
Okay. So
I'm there.
Thank you.
Hello, everyone. I welcome you all to my presentation. My name is Muhammad Fadi Abdelhaq from Al-Najah National University. I hope you will find this presentation interesting and informative. The main idea of this paper is to develop a powerful wireless sensor network for traffic monitoring. Traffic is monitored by a sensing system that can be placed adjacent to the road and can be used for vehicle counting, speed measurements, and vehicle classification. This system uses sensors that are sensitive to the magnetic field perturbation. Here is an overview of what I'm going to be talking about. I will start with a quick introduction to the problem that I'm working on. Then I'm going to be talking about objectives, system architecture, Transportation is one of the most important in the daily life of human beings that have a major impact on economy and social interactions. The most problem associated with the transportation is traffic congestion. As we know, the congestion and traffic delay are caused by number of vehicles on the roads or poor infrastructure of roads. Another main cause of traffic congestion is the traffic management system. The smart traffic management system can reduce congestion, for example, by controlling the traffic light dynamically based on the traffic flow parameters. So, the traffic management system offers the ability to obtain real-time information about the traffic flow. This information known as traffic flow parameters, which include number of vehicles, type of vehicles, and speed of vehicles. There are many types of traffic parameters detectors. The most common ones are inductive loop and video recognition. Each of these detectors has own limitation. For instance, video image detectors are sensitive to the weather conditions. On the other hand, deployment and the maintenance of the inductive loops need to cut off the road service and interrupt traffic vehicles. Both of them are expensive and they are not suitable for large-scale deployment. Also, both of them are developed by many researchers. The accuracy rate was not 100%. It could vary from 40 to 100% depending on the amount of data and weather condition. The objective of this research is to design and develop a system that measures traffic flow parameters and communicates them wirelessly from roadsides to the base stations. Once the data is available in the base station, it can be processed, analyzed, saved, and shared with other users, includes human or computer applications through the use of web services, which allow creating a smart traffic management system. This paper does not focus on measuring the traffic road parameters themselves. Instead, we used a simulated data to evaluate the system. The Earth provides us with its magnetic field that permeates everything between the south and north poles. Since our vehicles are made of metal parts, the Earth's magnetic field is disturbed by the movement of the vehicles. Therefore, we need a magnetic sensor that measures the perturbation in the Earth's magnetic field caused by the movement of the vehicles. The magnetic field is composed of strength and direction X, Y, and Z, which can be measured by the AMR sensors. The design of a traffic monitoring system consists of the software and hardware components. The hardware components consist of a wireless sensor network, magnetic sensors, and base station. The software component include a database to store the traffic parameters, a dashboard to visualize the traffic parameters, and web service interface to allow accessing the traffic data from other applications. As shown in the figure, the wireless sensor network consists of four main components: sensor nodes, coordinator node, base station, and internet server. Each sensor node contains Arduino microcontroller for processing data, 3 AMR sensors to be used as a sensing device, XP radio for wireless communications, power source, and XP shield used as XP Arduino adapter. The second component of wireless sensor network is the coordinator node. The coordinator is an XP radio connected to the serial USB port of base station using the USB adapter. Sensor nodes gather the data from their attached sensors and process it to extract traffic parameters, count, shape, and speed. Then communicate this data through a coordinator node to the base station. The application running on the base station gathers the information from wireless sensor network and communicates them to a web server on the cloud and save them in the database. As you see in this figure, this is a configuration of the sensing system which includes 3 AMR sensors placed on the side of the road to detect passing vehicles for the purpose of counting them and estimating their speed and size. Sensor 2 is placed horizontally in front of the sensor 1, and sensor 3 is placed vertically above sensor 1. The signal along the Z-axis have almost the same pattern for all types of the vehicles. Hence, the magnetic reading of Z-axis of sensor 1 used for detecting and counting the passing vehicles. Also, the speed of the passing vehicles can be estimated by using two horizontally spaced magnetic sensors, which are sensor 1 and sensor 2. If the distance between sensor 1 and sensor 2 is d, and if the detection time of sensor 1 is t1 and detection time of sensor 2 is t2, then the speed equal to the distance d divided by the difference between two detection times t2 and t1. Also, the height of magnetic disturbance reading of z-axis from 1 and 3 can be used to give an estimate of the vehicle size. These two flow charts show the system data flow. The Arduino microcontroller in each sensor node reads the magnetic field values detected by 3 AMR sensors, then determines if these values indicate the passing vehicle, the current time, and the vehicle speed and size are assembled into a bucket. Then send buckets to the coordinator through its XP. The coordinator node that connected directly to the base station computer through the USB port gathers the data from the sensor node wirelessly and passes it to the base station. For the base station application data flow, the application listens to the serial port. Once it reads a header byte, it knows it is a beginning of a new bucket and does some calculations to determine the source node ID and the received data. Then display the received data on the dashboard and save it to the database. To implement system. Sensor data were simulated by generating random data as an alternative to the magnetic sensors readings. Each sensor node generates a random vehicle speed drawn from the normal distribution and selects size of the vehicle randomly from list and set current time as detection time. Then it assembles the bucket from the simulated data and sends them to the coordinator node. The coordinator node receives buckets from sensor nodes and writes them to the serial port of base station computer. The base station application reads buckets from the serial port and extracts the traffic parameters from the buckets and stores them in a database. To evaluate the system, two base station applications have been developed. The first application reads buckets written on the serial port of base station and extracts traffic parameters from them. Also, it shows them on the screen with a statistical chart as well as saves them in the database. The second application retrieves the counter of traffic parameters collected from specific nodes from the database by giving two dates, two times, and sensor node ID. Parameters are displayed as statistical data in the form of pie charts and histogram. The top pie chart displays the distribution of vehicle speed at the specified date and time periods. The lower pie chart displays the distribution of vehicle sizes at the same date and time periods. The histogram in the right side of the figure shows the number of vehicles for each vehicle size in speed category. The conclusion. We provided an architectural design for traffic monitoring system that evaluate the main traffic parameters, traffic count, speed, and vehicle size. The information is necessary for designing and developing an intelligent traffic system. The paper focuses on the implementation of the wireless sensor network components of this system only. We are currently integrating the AMR magnetic sensors to be used in this environment. Thank you.
Okay, thank you very much for this interesting presentation, Mr. Muhammad. May I ask if any of the audience has a question? Okay, if there are no questions, I would like to just have a small clarification. If you could just explain how far are these sensors in your design, how far are they placed from your base station in order to avoid situations like delays in the data transmission, and this could cause data analysis at a very let's say earliest time, in the sense that the vehicle arrives at the traffic light, but still the data is not processed yet. Is there any parameter that governs that distance? I'm not sure if Mr. Fadi got my question. Okay.
Can you repeat the question?
Sure. I was asking if you have in your design a parameter that governs how far the sensors should be placed from your base station in order to make the analysis of the transmitted data in the proper time, in very adequate time before the vehicle arrives at the traffic light. Is there a specific distance or a parameter to control this distance?
Distance from themselves.
No, distance between the whole sensor assembly and the base station.
More than 100 meters.
Okay, and yeah, it sounds fair enough. That should be enough time for maybe analyzing the data before the vehicle arrives at the traffic light.
We can have router nodes to increase the distance.
Okay, yeah, that is for sure. And yeah, thank you once more for this interesting topic. I believe it's a very important component in smart cities, and the future is full of such applications, and we are in strong need for such research works. Thank you very much for your efforts.
Thank you.
Okay, we shall move on to the next paper. And this paper is entitled Smart System to Avoid Car Accidents. It's co-authored by Mr. Mohammed Safarini, Dr. Rasha Safarini, and Dr. Issam Ishaq. The presenter will be Dr. Rasha Safarini for today's paper. She is currently finishing her PhD degree in Information Technology Engineering at the Arab American University, which is jointly, I gather, it's jointly offered by with Palestine Polytechnic University and Al-Quds University. She has obtained her master's degree in computer engineering from Al-Quds University and her BEng in computer science engineering from Palestine Technical University, Khadouri. She has an interestingly diverse educational and research background. It's covering image analysis, processing, embedded systems, and IoT. Without any further ado, if Dr. Rasha would like to present live, or alternatively, Dr. Aiz, you may play the video.
Hello everyone. Our research is Smart System to Avoid Car Accidents. I am Rasha Safarini. My colleague is Mohammed Safarini. Our supervisor is Dr. Issam Ishaq. I will introduce our research to you. Then I will talk in details about the two parts of our system. Our system is comprised of two systems, which are Smart Road System and Smart Car System. After that, I will play a demo of our project. Finally, I will show you results, conclusion, and future work. There are several reasons that cause car accidents. Some of them are inside the car. The others are in the environment around the car. To reduce and avoid car accidents, we should focus on solving these problems. To do this, we proposed our project, which consists of two systems. One of them deals with the environmental problems. The other focuses on solving problems inside the car. As we can see here, each part of our system consists of Arduino, Raspberry Pi, and Raspberry Pi connected with each other to read data, exchange it between the two systems, and a web server which connects the two systems with each other. Here we can see the assembled system. Here we have the Raspberry Pi of the Smart Car system, the Raspberry Pi of the Smart Road system, the Arduino of the Smart Car system, the code of the Raspberry Pi, and here also the code of the Raspberry Pi of the other system. Finally, the Arduino of the Smart Road system, and sensors of our systems. Smart Car system focuses on studying factors inside the car that may cause accidents and study the awareness of the driver. We used several sensors for this task, such as DHT22, a humidity and temperature sensor, web camera, and gas sensor, MQ2. Also, we used actuators such as gear motors, which represents the wheels of the car, servo motors, and lids. Here we can see the connections of the Arduino with the used sensors and actuators. This is the Arduino and the gas sensor, the servo motor, the gear motors, and the lids that represents the lights of the car. The Smart Car system contains several sensors and actuators, as we said before. These sensors is used to read information and take actions when a problem occurs inside or outside the car. The first part of the system is the video camera, which the first part of the system is the video camera, which is positioned in front of the driver. The camera captures images continuously and sends them to the Raspberry Pi to analyze them. The Raspberry Pi detects the driver's eyes from the images and analyzes their status to decide if they are opened or closed. If the driver's eyes are opened, then the system does nothing. Otherwise, the system analyzes more image frames. In the case the eyes are kept closed for more than 2 seconds, then the system realizes that the driver is sleeping. Subsequently, the Raspberry Pi takes 2 actions. Firstly, send a signal to the Arduino to turn on the alarm. Reduce the car speed until the car is stopped unless a new signal is reached that the driver woke up. The second action is sending a signal to the web server to contact the smart road system to open the smart pumps on the road. This will make noise, which helps in waking up the driver. The second part of the first system addresses the probability of the decrease of O2 in the car and in turn increase the amount of CO2 gas. Additionally, temperature rise in the car poses a danger and increase the probability of making the driver sleepy and increase the probability of car accidents. So, to avoid these problems, DHT22 and MEQ2 sensors are used to continuously measure the temperature and O2 and CO2 concentrations inside the car. The Arduino reads the measurements of these sensors each minute and decide if it's normal or not. If the readings are normal, then no action is taken. Otherwise, send a signal to the servo motor to open the car windows. The second system of the whole proposed system is the smart road system, which focuses on studying the environmental factors that may cause accidents. This system also has several sensors and actuators, which works to reduce the probability of car accidents. The used sensors here is DHT22, humidity and temperature sensor, and photoresistor. The actuators are gear motors and servo motors that represents the smart pumps on the roads. Also here we can see the connections of the second system, the Arduino, the sensors and the motors, and the LDR, the DHT22, the connections between them and the Arduino. The system works in 2 aspects. First, when the web server receives a signal from the smart car system indicating that the driver is falling asleep, it sends a signal to the Raspberry Pi of the smart road system. This system in turn sends a signal to the system Arduino that guides the servo motor to open the smart pumps in the road. The pumps remain open until a further message comes, stating that the driver has awakened. The second part of this system studies and analyzes the weather conditions to know if there is fog on the road ahead of the car, because of fog impairs the driver's vision, which also increases the probability of car accident. The system has a DHT22 sensor to measure the temperature and the humidity in the environment around the car, and a photoresistor LDR to measure the light intensity. The Arduino reads the values of these sensors and analyzes it. If the measurements are in the normal ranges, nothing is done. Otherwise, the Arduino sends a signal to the Raspberry Pi that there is a fog ahead, which in turn directs the message to the web server to communicate with the smart car system to turn on the lights of the car. Finally, each 5 minutes, the system reads the photoresistor reading. This value is used to exchange messages between the two systems to make sure that the lights of the car are turned on during the night. In the whole system, we used two types of network connections. The first one is wireless communication using Wi-Fi. This type of communication needed when the two systems required to communicate with each other, and when the Raspberry Pi and the web server wants to communicate to exchange messages between them. The second type is the wired communication, which is the serial communication between the Arduino and the Raspberry Pi. As a conclusion, car accidents increased these days. To avoid car accidents, we should avoid its causes. To achieve this task, we proposed a system which comprised of two systems, smart road and smart car systems. Several sensors and actuators are used in each system to achieve this goal. The two systems work with each other to avoid and reduce the probability of car accidents. Now, we will play a demo of our proposed project. You can see here, when the driver eyes are closed more than 2 seconds, the buzzer starts and the smart pump open. Also, the car goes slowly until stop. As we can see here, the smart road system reads the humidity and temperature. Because the humidity is very high, sends a message to the smart car system to turn lights on automatically. When the smart road system detects light using LDR, the lights turned off automatically, and vice versa. Also, when the humidity is very high, the smart road system receives a signal to open a fan in the road to reduce the humidity and the temperature of the roads. And vice versa, when the humidity and temperature goes low, the fan is stopped. Inside the car, the smart car system, here when the gas sensor detects increase in the CO2, it sends a message to the servo motor to open the windows. Finally, we developed an Android application to display the read data from the sensors to the driver. As we can see here, this is the Android application and the data read from the Arduino.
Excellent. Was that the end of the presentation? Thank you very much, Dr. Rasha. Very interesting paper. And I would like to ask if any of the audience has a question. Okay, if there are no questions, I have a small comment. What you've presented is very interesting, and it shows how these technologies can be employed in the future. the whole lot of sensor networks and wireless communication in order to make the driving practice safer. I would be worried a little bit about the time response of the system in terms of taking the action. Usually they say it takes about 1/4 to 3/4 of a second to respond to an event on the road. If it doesn't happen within that time, an accident would occur. My major comment on this great work would be maybe to focus, if you haven't considered, to focus more on controlling the internal factors of the car to make it more smart, rather than focusing on the infrastructural level, because response time would be a major concern there. And also, if you're listening Russia and taking notes, and also I guess the cost of implementing the thing will be massive if you want to target the infrastructure. One of the things maybe you would think, I'm sure you thought about a lot of sensors, maybe the grip force on the steering wheel of the driver. That is another factor that you should consider when you want to detect if the driver is falling asleep or not. There are plenty of opportunities in this field. It's a very great work, and I'm happy to see that in Palestine, the applications of IoT and wireless sensor networks is starting to make a leap forward. I would like to congratulate you and your supervisor and co-authors on this work. Thank you. Shall we, if Rasha or Dr. Issam want to comment, you're welcome. Okay. Can we make it to the next? Yeah, next paper. Dr. Issam, would you like to add something? I congratulate you. You're the maestro of this session, Dr. Issam. MashaAllah.
Thank you, Dr. Ahmed. Actually, I have no comments. What you mentioned are actually, of course, very valuable inputs for further research. You already mentioned that we're just picking up the research. We're just opening doors, which is good, but there is plenty of things to do.
It's out of my amusement, actually. Stuff like that for us as engineers amuses us, and we feel so happy to see things like that starting to take place in Palestine. Excellent. Okay. The next paper, third paper of today's session, is entitled Improving Irrigation by Using a Cloud-Based IoT System. And it's authored by Dr. Rasha Assaf and Dr. Issam Ishaq. Another Dr. Rasha for today. She is currently finishing her PhD degree in Information Technology Engineering at the Arab American University, jointly with Palestine Polytechnic University and Al-Quds University. She obtained her master's degree in computer science from Al-Quds University, her BSc in Computer Information System from Al-Quds Open University. She has an interestingly diverse practical and professional experience as a lecturer and the head of the Technical and Engineering Department at Al-Ummah University College. She has research interests in dynamic information resource management, web and cloud-based IoT systems. Without any further ado, we may play the video, or if Dr. Rasha is with us, she can present her paper live. Dr. Ayes?
Maybe if she is with us, we can promote her to be panelist.
Yeah.
If not, also Dr. Issam is with us. He also co-author.
I guess I have the video as well.
Yes, I can run it. It's ready.
Yeah, as you wish. It's interesting to see women in IoT. This coincides with what Dr. Safa Nasruddin was talking about in the earlier session about enabling and empowering females, Palestinian females, specifically in the areas of technologies and IoT. I would say this session is dominated by female researchers, which is an excellent thing. Dr. Ayaz? Yeah.
Asaf, a PhD student. I will be presenting my paper as titled Improving Irrigation by Using a Cloud-Based IoT System, presented by Rasha Asaf and Dr. Isam Ishaq. The outline: motivation, introduction, the proposed system, conceptual design for irrigation system, area of utility, system feature, system component, hardware and software, cloud platform, flowchart, block diagram, electric circuit diagram, discussion, and future work conclusion. The introduction: combining both advanced technologies in hardware and software, the Internet of Things is able to track and count everything, which can incredibly decrease the cost and waste. The IoT transforms the agriculture industry and enables the farmers to assert with their challenges. Inventive applications can address this problem and therefore increase quality, quantity, cost, and sustainability effectiveness of product production. Motivation: rainfall levels have been dropping in Palestine over the last few years, and spring water flow has been decreasing and unpredictable. Increasing demand for food needs. Agriculture become an important factor in the economy. Limited the amount of workers to cover a large area of farm and limited time. To overcome the limitations of the irrigation system in conventional farming, and to provide and maintain the crops in their optimum environment for growth in terms of soil moisture and temperature. The proposed system is programmed and connected in a star topology. Two sensors send the extracted data to the server at predefined time intervals in minutes, depending on many factors such as weather, the type of plants. The information is sent by Wi-Fi to a Blink server. The information is summarized and displayed to the user through an application interface. The user can take various actions such as controlling the irrigation system via the application interface. The conceptual design of irrigation system. The components is connected together as shown. We have the PC, cloud storage, the microcontroller, water tank, soil moisture and temperature humidity sensor. Area of utility. The primary factor of this project is to help the farmers and reduce their work. This model can be implemented in perennial plant irrigation land and gardening land. System feature. Compared to other approaches, my proposed approach is simple, does not require configuration and IoT knowledge. It also provides simple to use interface to customize different aspects of the system. The system components, the hardware and the software. The hardware components the ESP8266 Wi-Fi model, which is a complete and self-contained Wi-Fi network solutions that can carry software applications or through another application processor and install all Wi-Fi network capabilities. The relay switch, which is an open and closed circuits electromechanically or electronically. Soil moisture sensor. This sensor can read the amount of moisture present in the soil surrounding it. And the second component, no, we're still in the first component, the hardware. We have the DHT22 sensor, which is a basic low-cost digital temperature and humidity sensor. The last one is the DC motor pump, which as it's the DC motor is any of a class of rotary electrical motors that convert direct current electrical energy into mechanical energy. And the fan. The main role of the fan is to harmonize the temperature and the humidity of the air, as it works on generating an internal air steam, unlike when there is no fan. And with the presence of an air steam, the air humidity will be reduced, and this will also reduce the occurrence of fungal diseases. This will also increases the gas exchange on plant leaves, so that it reduces the accumulation of carbon dioxide during the morning, and in the night it reduces the accumulation of oxygen. The software component. Arduino. The irrigation system is written in Arduino C using the ESP8266. The Arduino is connected to the microcontroller to send the soil moisture and humidity. Blink is an Internet of Things platform aimed to simplify building mobile and web applications for the Internet of Things. Cloud platform. The Blink server is used for building web applications and mobile applications using an open source in Java server. It's considered as an appropriate platform for IoT applications to send and receive messages between Blink mobile application and different microcontroller units. The flow chart, as it's shown here, we have here. It starts here. The ESP giving instruction, sensors detect the soil, moisture, and temperature, data sent to the cloud, login from the PC or smartphone, user's interface, depending on the level of the moisture and the temperature in the soil, the fan will work and the pump will work on, off, depending on the level. The parameters are adjusted back to reasonable levels. Sensors measures the parameter. The electric circuit diagram, as shown here. The advantages of our paper is water conservation, real-time data give, lowered operation costs, efficient and save time, increase in productivity, and to reduce soil erosion and nutrient leaching. The challenges, there is many challenges like the complexity. The IoT is a diverse and complex network, privacy and security issues, laser employment of manual staff or unskilled workers, equipment is costlier, and the awareness of the Palestinian farmer for this technology. Discussion and future work. There are many challenges in building automation systems, depending on many factors as controlled by farmers, such as many factors as collected by farmers, such as soil type, weather, humidity, transplant type, like citrus fruit, seasonal fruit, and vegetables. Irrigation time, as it is recommended to thrive the plant at the time of budding. In the future, we recommend to build a database including all information about all the above mentioned factors for the crops in Palestine by classifying the plant into many categories such as mentioned above. That will make the farmer feel safe and in using the automation irrigation system. Our conclusion. I conclude that this system is easy to implement and time, money, and manpowering saving solution for irrigation field. A farmer should visualize his agricultural land's moisture content from time to time and water level of source is sufficient or not. IoT-based smart irrigation system displays the values of the sensors continuously in a smartphone or on computer's web page, and farmer can operate them anytime from and anywhere. Thank you.
Thank you very much, Dr. Rasha, for this interesting presentation. It's a very important application area since, as you introduced at the beginning, Palestine suffers in many areas from the scarcity of the water resources. So it's important to intervene using such technologies in order to optimize the process and use the resources wisely. I'm not sure if any of the audience has a question for Dr. Rasha.
Maybe I have a question.
Sure.
It's well known that internet quality are not so good, especially maybe in rural area where most agriculture happen. Okay, so I don't know if the internet quality, how the whole system is affected. If the internet quality is bad or not available in certain cases, will the system stop, or are there maybe something like emergency plans?
Rasha, are you here to answer, or should I? Okay, so I think I can give you an answer. So actually, the internet quality, of course, it's a important factor, but especially in this system, it's not really like the car accident system where you have to have very fast reaction. So it's actually tolerant to short disconnections. So even if you're disconnected for even a few minutes, it will not hurt anything. You're just either irrigating a little bit too much or a little bit less. And also,
can the system be autonomous alone?
Currently not, but it's easy to do. It's easy to do. This is an easy extension. So if there is no connection, that to continue working as is. But also what I wanted to say, it's the amount of data that is transferred is actually very little. So using technologies like, for example, LoRaWAN, which is still not available in Palestine, you could reach rural areas with a single cell up to tens of kilometers with a single cell. It's not like Wi-Fi. So it would be sufficient with these technologies. With Wi-Fi, of course, you need better connection, or with GSM.
Thank you. Very informative answer, Dr. Issa.
Very interesting, as I said at the beginning, and what should I say? It's true that this process is not time critical as the car accident process, but I would say maybe it's an environmental critical application where maybe all modular should be well protected. And I would go about a modular design, Dr. Issa, in such systems, because it depends on the customer needs in different areas. So modularity in implementing the design would be a good thing to consider. I congratulate you once more on this very interesting application.
Yes, definitely, I agree with you. It should be modular.
Thank you very much. We shall move on to the next paper, the fourth paper of today's second session. It's entitled Cloud-Based Internet of Things Approach for Smart Irrigation System, focused on the design and implementation. The paper is co-authored by Dr. and Dr. Issa Ishaq. Dr. Thaer is currently finishing his PhD in Information Technology Engineering at the Arab American University. It seems that this program is very famous, and plenty of applicants are enrolled with his previous colleagues. He received his BSc in Computer Engineering and MSc in Advanced Computing from Al-Najah National University. He has research interests which include evolutionary computation, meta-heuristics, data mining, and machine learning. So let us all together listen to his interesting topic in the field of agriculture as well.
Assalamu alaikum. Welcome everyone. My name is Thaer from Al-Quds University. First of all, I would like to thank the Committee of International Conference on Promising Electronic Technologies for their great efforts and excellent organization. In this presentation, I will introduce our paper entitled Cloud-Based Internet of Things Approach for a Smart Irrigation System, Design and Implementation. This research has been introduced by me and Dr. Issa Ishaq from Al-Quds University, Palestine. These are the presentation outlines. I will talk about the problem statement and suggested solutions, motivations of the study, the proposed system architecture, our main contributions, the system design and implementation, and finally conclusion and future directions. Water plays a significant role in the economic development of countries. The availability and accessibility of fresh water creates opportunities for developing countries for sustainable economic growth, social and environmental benefits. In our country, Palestine, water scarcity is considered one of the most critical problems for environmental and political reasons. As water resources are limited, and the Israeli occupation controls most of them. According to the Food and Agriculture Global Information System, 69% of the fresh water is consumed by the agriculture sector at the worldwide level. Farmers often use traditional irrigation systems to water their crops. These systems are ineffective. They consume a lot of time and effort, especially when several fields are distributed in different regions. Moreover, traditional irrigation often leads to the problem of over-irrigation and hence consuming large amounts of water. It also may cause an under-irrigation problem that negatively impacts the quality of crops. These problems can be handled by adapting modern technologies to build smart automatic irrigation systems, which have recently attracted considerable interest in the agricultural domain. The proper design and installation of an automated irrigation system have many benefits compared to the traditional one. It will schedule the irrigation process in an optimal way and thus contribute to reducing time, effort, and cost. It also saves significant water while improving plant quality with less human intervention. The availability of innovative technologies such as Internet of Things, sensors, wireless sensor networks, and embedded processing significantly contributed to building effective irrigation systems. These technologies allow generating a vast amount of data that can be stored, visualized, and analyzed to extract useful knowledge that will improve the overall planning strategies and decision-making process. The proposed solution, if it is generalized, especially in developing countries, will contribute to achieving two of the Sustainable Development Goals. First, it will ensure goal number 1, no poverty. Second, it will partially ensure goal number 6, clean water and sanitation. These facts motivate us to provide this solution at the global level and also encourage us to provide a solution that contributes to the exploitation of our local water resources in Palestine, which suffers from the water scarcity problem. Now, let's present the proposed system architecture. The proposed system can be divided into three main subsystems that cooperate to achieve the purpose. The first part is wireless sensor network. The second part is central processing unit, and the third part is cloud computing services. The wireless sensor network consists of interconnected sensor nodes that communicate wirelessly to collect data about the surrounding environment. In this project, the main parts of the wireless sensor network are sensor nodes and the coordinator. The sensor node is employed to gather data from different types of sensors. As we can see in this figure, we use two types of sensors as a sensing unit. The first sensor is YL69 moisture sensor used to measure the humidity of the soil. The second sensor is DH22 that utilized to measure the relative humidity and temperature. As a processing unit, we used Arduino Uno to read the input values of connected sensors and send them serially to the connected transceiver component. For a wireless communication, we employed XP-Zigbee module, which configured to ensure the safe delivery of the collected data to the targeted node. The second subsystem of the proposed framework is the main control unit, contains of Raspberry Pi, a coordinator XP module, and a solenoid water electrical valve. The primary purpose of this node is to collect data from the remote devices, analyze them, and control the irrigation process. The major tasks of Raspberry Pi are read data from the connected coordinator XP module and then analyze the gathered sensors quantities. Based on the analyzed data, it will provide the proper decision whether to irrigate or not by controlling the electrical water valve. Finally, the collected data are transferred to cloud using ThingSpeak API. To improve the effectiveness of the proposed system and to benefit from the cloud services, we use ThingSpeak IoT Cloud, which is an IoT analytical platform cloud service that can be utilized to aggregate, visualize, and analyze live data streams in the cloud. It provides farmers and interest persons with a live streaming platform to monitor the status of the plants, create instance visualization, and sending alerts. So in this paper, the major contributions are summarized as follows. Transferring the measured quantities by moisture sensors wirelessly to the Raspberry Pi, a wireless sensor network using XP modules is utilized to achieve this task. The gathered data is transferred to the cloud for storing, visualizing, and monitoring the agricultural parameters. The system provides efficient automated irrigation that ensures high quality of crops, saving water and reducing human involvement.
Excellent. I guess very short and
Now let's
concise
briefly present
question.
the hardware and the software components of the proposed prototype. The proposed prototype was designed and implemented using different hardware and software components as follows. Raspberry Pi, Arduino Uno, moisture sensor, humidity and temperature sensor, XP and XP Explorer dongle, power supply, 2-channel relay module, and solenoid electrical valve. In software, we used XCTU to configure the XP, Arduino IDE, ThingSpeak IoT platform, and REST APIs. The Arduino is programmed using IDE and C++ programming language, while Raspberry Pi was programmed using Python. Actually, at this phase of the project, we were interested to verify that the proposed model is working properly in all its parts. The tested prototype shown in this figure is composed of a wireless network consisting of 2 nodes. Each node controls the irrigation of a sample of soil when needed and storing the gathered values in the cloud for monitoring and obtaining graphs. These are samples of data collected over a period of time as well as the live data streams visualization obtained from ThingSpeak platform. We can easily monitor the fields and know the condition of each one, as well as the values of humidity, temperature, and decision taken in each case. When scaling up this prototype and apply it on real fields distributed in different regions, the gathered data can be utilized to extract hidden and useful knowledge by employing data mining and machine learning techniques. This helps farmers and others for planning and decision making. It also helpful for early prediction purposes. In this paper, an efficient cloud-based IoT framework for controlling and monitoring the irrigation process was designed and implemented. The main objective is to save water and improve the quality of crops. After inspecting the prototype, many challenges are posed. Soil is different from place to place, and this poses a challenge to choosing the right sensors and also the right values. Judging whether the amount of water in the soil is sufficient or not varies with different crops. Consequently, it is necessary to rely on the experience of farmers and the previous studies to build a database for the various crops so that the appropriate settings are determined for each crop. The number of sensors that should be used and perfectly distributed is a big challenge. Therefore, artificial intelligence techniques must be employed to find and estimate the optimal number of nodes to cover large areas. The humidity sensor must be carefully calibrated and extensive experience should be applied to have the required accuracy. In addition, wireless sensor networks have many challenges such as security issues. For future work, extensive experiments will be conducted on real crops and analyze the resulting data using machine learning to obtain useful recommendations. A comparison can be performed with the traditional irrigation systems in terms of water consumption and the quality of crops to ensure the effectiveness of the proposed model. Moreover, the system can be adapted to consider more environmental data by adding different types of sensors. Thank you for listening.
Thank you very much, Dr. Thaer. Another interesting speech or presentation about applications in the agricultural field. I wonder if any of the attendees has a question for Dr. Thaer. Okay, if not, I guess the same maybe recommendations made earlier on the similar implementation in terms of implanting the sensors in the soil and maybe routing the wires. I guess there will be a major concern in that area. Maybe your future work, I would like to see in the future that you have taken the environmental factors into consideration in implanting your sensors in the soil. I've also posted a website on the chat box if you would like to visit their range of products. They have very interesting products covering the range of sensors that would be applied in this area. I wish you every luck in your future research endeavors. Shall we move on to the next paper? Okay. The fifth paper in today's session is entitled Online Monitoring Health Station Using Arduino Mobile Connected to Cloud Services, specifically a subtopic on the heart monitoring system. The paper is co-authored by Dr. Iman Abdelkarim Karaja and Dr. Issam Ishaq. Dr. Iman is also currently finishing her PhD in Information Technology Engineering. She obtained her master's degree in Scientific Computing from Birzeit University and obtained her bachelor degree in Computer Science, Computer Systems Engineering from Birzeit University as well. She works currently as a computer engineer at the Ministry of Labor, and she has research interests in the health-related technology, systems, and applications. Yeah.
Hi, this is Iman Karaja. I will present our paper, which is titled as Online Monitoring Health Station Using Arduino and Mobile Application Connected to the Cloud Service. In our presentation, I will present the introduction, the proposed system components, which consist from the electronic circuits, which consist from the heart rate sensor, the body temperature sensor, the HC05 Bluetooth module, the electronic circuits schematic diagram. Then I will talk about the Arduino Uno, then talk about the Android application, then the Google Sheets cloud. Then I will talk about the system architecture, which consists from the system block diagram and system software flowchart diagram. Then discuss the results, then conclude the work. Okay, as an introduction, as the world suffers from the COVID-19, which is a newly discovered coronavirus that have been officially announced as a pandemic by the World Health Organization in the March 2020. It's a new virus in the medical care that has no specific treatment until this moment. Believing in the importance of the using electronic and technological development to raise the level of the healthcare, our system idea came to design the online monitoring health station, which displays the vital data in real time, including the accurate measurements of the heart rate and body temperature, and special alarm system without the need of going to the hospital. Monitoring the vital signs of a human body, including the body temperature, the heart rate, respiratory rate, the blood pressure, and the saturation of blood oxygen, are very important since they help assess various body functions and indicate the potential diseases. In our system, we connected an electronic circuit to build a mobile phone that stores and displays the vital data of the heart rate and the body temperature in real time in a cloud service, which made the monitoring process easier. It sends an alarm when the readings are abnormal and makes an auto call after five abnormal readings. We will present the software and the hardware implementation. The proposed system components. The heart monitor system consists of the following hardware and software components: electronic circuits, the Arduino Uno, the Android application, and the Google Sheets cloud. Let's talk about the electronic circuit. The first part in the electronic circuit is the heart rate sensor. The heart rate sensor, the SN11574, is an optical heart rate sensor that measures the heart beats per minute. The changes in the blood volume in the orient related to the changes in the intensity of the reflected light through it. Our system adapts the reflective mode for the light source and the detector as they are adjacent to each other and the person's finger placed in front of the sensor. It should be noted that the heart rate sensor is provided with filter to reduce the noise and increase the accuracy of the measurements. The second part of the circuits was the body temperature sensor. I used the LM35 sensor, which scale factor is 0.1 voltage per Celsius. The third the third part is the HC05 Bluetooth module. Bluetooth is a wireless technology designed to replace the wire connection. HC05 module is based on the Bluetooth technology to connect the electronic circuits with smart devices like smartphones. HC05 module communicates with the Arduino Uno using a serial communication. We use the default setting of the HC05 Bluetooth module that can be changed by the ATM commands. This module will have the following pin configuration: the enable, the TX, the RX, and the VCC. The data is transmitted to the phone via Bluetooth using the Arduino Uno and displays the readings on a mobile screen. This is the schematic diagram for the electronic circuit. In our system, we use the separated power supply to avoid the noise caused by the Bluetooth module. The heart signal is too small and sensitive, so they can be easily affected by any noise. The Arduino Uno. The Arduino Uno development board, which contains 80 mega 328 microcontroller used to calculate the number of the heartbeat per minute. It also measures the body temperature and send the calculated values to the Android application via HC05 Bluetooth module. If the signal voltage is above the threshold voltage, then it's considered as a heartbeat. Software code had been written using the Arduino C programming language, which contains a specific library to measure the heart rate and communicates via Bluetooth module. the Heart Monitor Android application. The Heart Monitor application has been created on the online platform MIT App Inverter. This application displays the patient's parameter, which are the heart rate and the body temperature. When the heart rate value is abnormal, less than 40 and more than 120, the application will make an alarm. Then after 5 abnormal readings, it will make an automatic call to the specific phone number that can be a patient's companion number or the healthcare professional. This screenshot presents the Heart Monitor application. The Google Sheets Cloud. In order to make all vital values available for the medical staff, we use the Google Sheets Cloud to sense heart rate and body temperature and store them in the cloud. Google Cloud Service is free and supports real-time feature. And this screenshot presents the Google Sheets Cloud. The system architecture. Okay, let's talk about the system block diagram. The heart rate and the body and the temperature sensor gets a non-numerical value from the patients. The Arduino microcontroller processes the data and convert it to the numerical values. The numerical values can easily send to the mobile phone using the Bluetooth module, the mobile phone using the internet connection, and the web viewer component connected to the cloud. After that, results can be monitoring from anywhere, have internet connection through a special link in Google Sheets. Okay, the software flowchart diagram. The flowchart diagram presents step-by-step implementation for our system. Firstly, send analog voltage proportional with the heart rate and temperature value from sensors to the Arduino. Calculate the heart rate and body temperature value using the Arduino code. Send data in mobile via HC05 module, which is Bluetooth. Monitoring the vital values and switching an alarm when the heart rate value is getting abnormal. Makes an auto call for a specific number when the heart rate staying abnormal for 5 consecutive times. Sends data to the Google Sheets Cloud to be available for the medical staff. The results. To make an accurate result, we fix the heart sensor around the patient's finger using a dark piece of plastic to avoid readings error caused by the motion or the light interference. We compare the result that we get from the heart monitor system with an ECG device in the cardiologist clinic to compare the accuracy of the system. The error rate calculated by finding the difference between the measured value from the HR sensor 11574 in our system and the known value from the ECG device divided by the unknown values. Okay, in this table we showed a comparison result between the ECG device and the heart rate sensor 11574 for the 5 patients at the cardiologist clinic. By calculating the arithmetic average value, the error rate is 2.56% and the accuracy of the heart rate sensor is 97.4%. As a conclusion, we can conclude the work as follows. Monitoring the human vital signs such as heart rate and body temperature is important for people who have critical health situation, and they can be an indicator to other diseases. Heart monitor system shows a high accuracy result compared to the same readings measured by the ECG device. The measured value are displayed on a mobile phone using the heart rate monitor application. The results are stored and displayed in a cloud service simultaneously for a continuous and real-time monitor to the patient's heart rate and body temperature by the medical staff anywhere and anytime without the need for going to the hospital. The system will make an alarm and automatic call for a registered number when the measured values are abnormal, using the Android capabilities programming without a need for going to the hospital or even a person to monitor the patient's health. Thank you very much.
Well, thank you, Dr. Iman, for this interesting presentation. I think it was clear and very organized, well organized. Any questions from the audience? Okay, maybe I have a small comment or a question. I can see that this is a very interesting implementation of a wearable system. At least in the future, this device or this system can be altered in a way to become a wearable device. And therefore, I can see a potential application in what usually doctors prescribe as a 24-hour monitor for some patients to discover and find out if they have a chronic cardiac disease, rather than relying on measurements made in the clinic. So they deploy the system with the patient to the house, and they leave it with them for 24 hours to record all ECG or cardiac behavior of the patient. If you can consider storing the data on the mobile phone as well, instead of relying on storing it on the cloud, maybe it will have a potential application in diagnosing certain diseases in the future, rather than focusing on emergency situations only. And I can see it has great potentials in that area. Dr. Issa, if you have any comments on
thank
this.
you. This is actually a very nice idea. And I think it's very easy to extend the system to do that. So just keep a local copy, and then it also helps. For example, when the internet is disconnected, then the data is stored temporarily on the mobile phone, and then it's transferred to the cloud once connection is restored. I think this is an excellent idea.
Yeah. It will be a cheap thing and readily available for everyone, because everyone now has a smartphone, and doctors and health system will benefit a lot from that. Yeah. Excellent. Great. So we move on to the last paper of today's session, entitled Design and Implementation of Monitoring and Control System for Poultry Farm. The paper is co-authored by Dr. Izzuddin Adwan, Mr. Muhammad Abu Qasim, Mr. Saeed Abu Rous, and Dr. Muhammad Al-Najjar. And our presenter for today is Dr. Izzuddin Adwan. Needless to mention all of his achievements and remarkable career, I'd like to say a few words about Dr. Iz. He received his BSc degree in electrical engineering from Berzeit University, and the master's degree in electrical engineering from Oklahoma State University back in 2003, and his PhD in electrical engineering in 2013 from the University of Siegen in Germany. He is currently an assistant professor and head of scientific research department at Palestine Technical College in Deir el-Balah. He co-authored and authored more than 40 scientific papers in journals and international conferences. His main research interests are in the sensors, inertial navigation systems, and control systems, mobile robotics, sensor fusion, and applied estimation theory. Pretty diverse and interesting research interest. He is the recipient of Fulbright and that scholarship. He is the PI and the coordinator of several European Erasmus Plus projects. And last but not least, I'm pretty sure you all know that he is the founder of the IEEE International Conference of Promising Electronic Technologies since 2017. And he's been running the show, the interesting show, since that time until today's conference. Without any further ado, I'm very honored to present Dr. Iz to talk about his research work. تفضل.
Thank you a lot, Dr. Ahmed, for this very nice introduction, and it's well done. So I just want to maybe to add a note here. This work also includes 3 more authors, but maybe this was the old version. So this work is interesting because it combines the academic work with professional work. It's not only just a model or a simulation, rather it contains real implementation, as it's clear in the title. So this work combines academic work and industrial work of real poultry farm. Let me start with giving the content. I will start with introduction, problem statement, objectives, methodology, system description, and end with results. Introduction. The poultry products in the Gaza Strip considered as one of the highest nutritional value products, and the demand for the chicken meat is constantly increasing. It's clear because the population is increasing. We are now exceeding 2 million in the Gaza Strip. According to statistics, in the year 2018, there are more than 1,500 economic farms for raising poultry. The number might seem to be big, but it's not the case, because we at the Gaza Strip consume monthly from 1.7 million to 2 million chicken monthly. So this number might be reasonable, having 1,500 economic farms in the Gaza Strip only for raising, and also 284 farms for producing table eggs. Mostly the problem here are primitive designs of and the classical ones. So they are manual operating. Here, the problem statement: poultry farmers face many problems, and most of the problems come from unexpected weather variation over the year, or we call it weather fluctuations, which might cause diseases such as influenza and Newcastle. To improve poultry farms' performance, we develop a monitoring and control system for the classical poultry farms. Let me try to hide this here. To improve the environmental conditions for feeding and also for the weather. Objective of this work. There are 3 main objectives of this work. First, surveying existing literature for automation of poultry farms with focus on those which are PLC operated or microcontroller based. Second, We will analyze farmers' needs at poultry farms based on a survey and determine the technical requirements of an automated monitoring and control system of the poultry farms in Gaza. The third objective is to design and implement an automated real poultry farm and compare its growth rate results with the classical poultry farm and verifying the developed control and monitoring algorithms. In fact, in this work with my co-authors, surveyed a relatively large number of the farms, and I can summarize it as follows. PLC is used to automate the feed and water in one of the works, which are available in the paper, temperature, humidity, and odor control, and a low-cost manure collection system is implemented in that paper. One of the early approaches of using internet suggested the use of mail system. Some approaches describe wireless sensor network combined with GPRS to control temperature, water level, smoke, gas, and food dispensing. Usually, they use Arduino, and in this case, they use a Raspberry Pi to control and monitor all the data. Interestingly, they found that production can be increased by reducing mortality rate, and it can be accelerated to reach larger weight, around maybe 2 kilograms in shorter time. There are also an IoT-based system. Other implementation of low-scale poultry farms are done after simulation. Other control on focus on controlling gases, light, humidity, temperature. And most works, they use Arduino for controlling. I guess it's just a matter of developing something like a proof of concept, which is different from our focus. Our methodology relies on monitoring and operating the poultry farm. We first want to diagnose the problems faced by poultry farmers and identify their needs based on a questionnaire distributed to 30 farms. Based on the analysis of the questionnaire, we can decide on needed sensors and actuators to monitor and control the poultry farm. Sensory data can be displayed to the user. Let me here show some of the survey results. Climatic variation and the spread of harmful gases was one of the problems faced. Other is the having high mortality rate. It's around 14%, 13.95 on average. And there is a spread of many diseases among inside the farm, such as influenza, Gombro, and Newcastle disease. Here we can show these results. For example, heating the farm, some use 25% use wood, 37 use gas, 25 use electricity, and around maybe 13% they do not use any kind of heating in the farm. And also maybe for lighting system, some, let's say 70% use day and night, and 30% use only night lighting system. Identifying needed automated factor, let's say here answer yes or no. We ask the farmers, do you want the following sensor? Do you want monitoring 24 hours? 65% answered yes. 35 said it's not necessary. Ammonia sensors, 69 said yes, it's necessary. 31 said it's not necessary. Oxygen sensor, 90% said yes, it's necessary. And 10% said no. Temperature and humidity, 95% said it's very important. So there is large majority here agree on this factor, temperature and humidity. So we can see what are the important factors here from this questionnaire for the farmers. So we can describe the system. The system should have a main microcontroller or programmable logic controller, and it should have temperature, humidity, light sensor. What else we have here? Load cell can be also, and we control different parts of the system. We control, for example, ventilation system, feed, drink, manure system, birds collecting, heating, light, and we display the results either to the PLC itself, HMI, or to an LCD display. This is the main loop of the PLC program. It might be here, maybe we can zoom inside it if you like. Okay, we start, we run feeding and drinking system. If there is need for more feed or water, we add. If not, we keep looping. If temperature, there are like threshold values. If this is exceeded, then we run the actuators. So, and it keep loopings all the time. This is the real poultry farm as it is shown. Its design. This is implemented. So as we said, this is combining academic work with a professional one. So this is real implementation. Here we see the main electric boards, and this is further implementation. And the team working on this paper are professional and well known in the Gaza Strip for designing. My colleagues, Engineer Mohammed Abu Qasim, Engineer Saeed Abu Rous, they are well designed, professional engineers in this work, automation work, PLC based work. And here we show from inside the farm itself. This is called H-type cage system because it looks like H. They are parallel to each other and with equal area, each one. This is a ventilation system and its computation are shown clearly in the paper. I don't want to give details here because we have time limitation. This is continue for ventilation and for cooling bed and air inlets. This is here, let me move a little bit. This is a feed control system. Okay. And maybe I can make it full screen here. So this is bird harvesting system. You know, when the chicken are ready to be commercially distributed, this is automated system for collecting them. And this is really very interesting thing that we need to show here, to talk about. This here is a comparison between modern and classic poultry farm. And there are two common types of chicken are in Gaza common, which are cob type and roast type. And this here shows the average growth, and this is here per weeks. Okay. And it is clearly the automated farm shows efficient system. This parameter is called feed to meat conversion efficiency. On average, today we reach that a chicken needs roughly 1.5 kilogram of feed that is converted into 1 kilogram of meat. So here we reach in shorter time and in better efficiency, larger weight than the open farms for both types. So in conclusion, we presented requirements, analysis, and design of poultry farm monitoring and control system based on PLC. The proposed system helps the farmer to easily monitor and manage the farm so that they can monitor changes. To achieve this goal, we use different type of sensors, a range of sensors, and the system is able to display the environmental conditions of the farm. Thank you a lot for listening, and maybe we can now end the presentation.
Thank you very much, Dr. Izzeddin. Any questions from the attendees for Dr. Iz? He's present with us to answer any queries. Okay, I have a small comment, Dr. Iz, if you don't mind. In such a process, there are plenty of biological perspectives to pay attention to, and I appreciate the industrial approach that you followed in your research, and also the methodology by surveying the different solutions available in the literature. But I wonder if there are any biological measurements or measurements made on the individualistic level rather than the holistic picture of the whole farm, the chicken inside.
Yes.
Is there a subsystem which forces the chicken to pass through a certain gate to make some maybe temperature measurements or infrared readings, stuff like that?
Mm-hmm. This is, you compare something like with monitoring elderly houses, I think.
Kind of.
Yeah, but in our case, and this will be implemented as extension of this work, we will monitor the weight of the chicken itself. Each one, we plan to install and design and install a monitoring system for each chicken, so we can monitor day by day or even hour by hour how the growth is advancing, and if there are problems, we can maybe discover it early. If and this is one of the biological parameters that you maybe asked about. I think this is necessary, and maybe it is planned to be as expansion of this work, extension to it. And as I said, it will be a real system, because the farmers themselves need to know exactly if the desired weight has been reached, if it has been reached, now it's time to start distributing it commercially. And if they have indicator like this, they might save more money, because the growth happens in certain period, early period. Later it becomes slower and more costly. So
Yes.
regarding biological parameters, we have a plan in monitoring the weight. Other parameters, it can be considered, but it needs more sophisticated systems.
Yes, definitely does. Yeah. Okay. Thank you very much for this research, which I expect will have some impacts on the economy, since technology has proven everywhere to intervene in a way that saves time and money, and preventing or prevents some bad consequences or damages that could happen to crops or poultry or animals. Pretty interesting focus in this session on the use of new technologies, cyber technologies, I would say, or IoT technologies in the fields of agricultural applications, also in the medical applications. I would say that this opens the door, or very wide doors rather, for future research in Palestine, employing IoT, cyber technologies in different fields. The future is there, and in Palestine, it's becoming a trend. The last or the latest national forum held by the Higher Council of Innovation and Excellence was focused on the pandemic, and the one before that was focused on the fourth industrial revolution, where IoT is a major thing. And I would recommend at the end of this beautiful session that all young researchers to be more motivated and encouraged to take on academic degrees or research activities in the field. I'm very glad to chair this session. It's been very joyful, and I would say not every day you can sit in such a very rich environment and hear researchers talking about interesting results. Thank you all very much. If you'd like to take it over from here, Dr. Issa. Thank you very much.
Thank you a lot, Dr. Ahmed, for chairing this session. It is really very professional at chairing, and we are also on time. This session ended now.